Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. Welcome back to Copeland Theatre, where you don't have to cross the road to get here. It's all very good. Today we're going to get and do some R, and I'm going to show you a little bit about how you can get yourself going in R if you've forgotten. That's very loud, isn't it? But echoey. I wonder if I can change that. Hang on. Maybe I can't. Here we go. Is that better? There we go. Okay. So we're going to learn a bit of R, just you watching me. One of the things you'll discover is that R is definitely not something for voyeurs, right? Watching people use R is not exciting. Doesn't teach you much, right? And that's because of the fingers to brain connection, right? So when you're typing, something goes directly from your fingers up through your arms, through your neck into your brain, tells you what you're doing. Watching me do it, not quite so good. So what happens is when I teach R, we have the lecture, people sit there, they go, wow, that's great, I think I've learned the entire package, cool. Then they sit down to try to use it themselves and, right? That connection, finger to brain. Very important. So, I encourage you to watch me, but I'm going to encourage you to do stuff yourself as well, and I'll tell you how that's going to work. Now, before we begin, one of the things that I like to do in this course, most days, is to do something a bit fun. Now, you and I may end up differing in our opinion on what fun is. That could happen. But what I'm going to try and show you is interesting stuff from around the internet, on visualisation, because one of the core themes of this course is how do you effectively communicate information. And so yesterday we watched Hans Rosling's video, and that's one way you can look at information from around the world. But I'm going to show you over time different websites that I think are really cool, and that I hope you'll visit occasionally to see what's going on. So today I'm going to show you flowing data. So flowing data, so very simple URL, flowingdata.com. And this is the brainchild of a guy named Nathan Yao. Now Nathan did a PhD in statistics at UC Berkeley, and he discovered during his PhD in statistics that visualisation was a thing, and it was the thing that he was really interested in. And he's gone on to start this website, started it a few years ago, and since then he's actually published several books which have examples from the site and so on. They're all, if you look on Amazon.com, you'll find them. They're perennially among the best sellers because they're so cool. And he's a cool guy. I mean, must be cool, right? He's Berkeley, California, all that stuff. And he updates this site pretty much every day, right? Except on weekends, I think. And so there's all sorts of stuff you'll find here. And most of it comprises examples of visualisation. So we'll see a lot of examples. I'll scroll down and you'll see some. He's also got, and again, I'm not trying to sell anything here. You can actually join, become a member, which costs some money. But if you do that, you get access to tutorials that he's written. He does everything in R, and you could actually get tutorials on how to do certain things in R. And these are pretty vertical things. These aren't the sort of things that I'm going to show you how to do. We're going to learn to do fairly simple things in R. He's going to show you in his tutorials how to do much more vertical things. So, again, this all depends on how much money you have to spend on stuff like this, whether you're that interested, all that stuff. I get that. So I'll just point out that it's there. Okay? So you can see that yourself. Okay, so he's got some examples here, most common jobs by state. Okay, you can see this is a visualisation based on maps. Map data, by the way, is a very common form of visualisation currently, and it's largely available because of the fact that maps, well, it's all Google's fault, right? I've got my little Google hat on here. I was walking through town at lunchtime, and you know those people who stand around in town with carrying iPads? You know, the ones who really want to interview you or something? Anyway, I must look friendly or stupid, and so they always say hello to me. Anyway, the lady I was passing, said, "Oh, hello." I said, "Oh, hello." And then obviously I wasn't stopping. So she then says, "Oh, I like your Google hat." So I kept walking, and I just said to her, "Yep, it's a good hat. It's how I find my head." Yeah, okay. Anyway, well, okay. Anyway, I walked about another 10 metres, then behind me I heard her shriek in laughter. She actually thought it was funny. Okay, well, maybe she was trying to get me to come back. And then she screams out, "I just got it." So there you go, all very cool. Anyway, where was I going with this? It's all because of Google. You've heard of Google Earth, you've heard of Google Maps. Who here uses Google Maps? Oh, you really don't want to talk to me, do you? Oh my goodness. How do you get from one place to another? What do you do? Google Maps, right? Yeah, okay. So Google Maps have made maps of the world really, really common. They're on everybody's phone, okay? And so as a result, maps have become a really dominant form of visualisation, showing things on maps. Now, there's good and bad about that. You know, so one of the things we're going to do in this course is think about what's good and what's bad about different kinds of graphics. So let's just detour for half a second and talk about maps. So if you look at these maps of the United States, you'll sort of see, okay, they're colouring in states. And if states are a certain colour, then a certain thing is true, and so on, okay? The problem with maps, of course, is that the states are all different sizes, and the sizes are not proportional to population. I don't know what you know about the United States, but most people live on the left-hand side or on the right-hand side. Right? They're either in California or generally up in the northeast or down in Florida, okay? And there's pretty much nobody in the middle. It's a bit like Australia. Who here has been to the middle of Australia? Right, no, right. Who lives there? No. Why? It's hot. There's things that'll kill you. You've heard that Australia's got 20 of the deadliest animals in the world. They're all, not in Canberra luckily, although a kangaroo tried to kill me the other day. He did. I was riding my bike and he decided that I was in his way. Anyway, I managed to miss him. So deadly animals. Anyway, the US. No one in there, in the middle. So, you know, if you've got a state in the middle that's coloured green, you sort of get the feeling that that carries some weight, but that might represent 5 people. Whereas if you've got California coloured green, that's 30 million people. Okay, so, you know, maps don't work perfectly because of this inequity between population density and landmass, right? But they're a reasonable representation of spatial information, and so you'll often see maps. The other technique that this graphic uses, this is the first time I've looked at it, by the way, I haven't gone into his site today, this is the first time. It uses a concept called small multiples. This is another really interesting technique for visualisation. Small multiples produces lots of little graphs side by side. And this raises a really interesting point about the way humans perceive things. So you've heard of short-term memory and long-term memory, right? So if I show you 2 graphs on 2 separate pages and you have to turn the page to look at the second one, and I say to you, what's the comparison? You generally will not be able to do it properly, at least, without going back and having another look. Okay? And if I say to you, you can't turn back, you're stuffed. And I'll show you this. You might say, no, I'm smarter than that. Newsflash, you ain't. And that's not me being mean to anybody, it's me too, right? So we'll actually see some examples of that live later. So small multiples are a way to get around that. It puts everything on the same page, okay? Humans are good at side-by-side comparisons. They're not good at comparisons through time. We think we've got good memories. We generally don't. So I have a colleague in criminology who knows this, and what they do in their first lecture, first year criminology, is everyone's sitting here like you are, and then somebody, a perpetrator, enters the room from the back, runs down the front, does something weird, runs out. Okay? So it sounds pretty cool. Nothing violent, just something pretty weird. Then they do the eyewitness thing, right? So they sit down and say, okay, describe the person. And you should see how people describe the person. And you can lead them so easily. If you ask them, did he have a hat? Because you've said hat, most of the people in the room say, yes, he had a hat. Yeah, did he have a moustache? Yeah, I think he did. And you get literally everything on the planet. And that's because your memory, your short-term memory, just isn't designed to hold that kind of information. Same with graphs. You look at a graph on one page, and even if you're looking at it thinking, you've got to remember this, as soon as you turn the page, you look at a different graph, gone. Okay? And this happens throughout all sorts of different parts of cognition. Almost everybody's had the experience, I think, of sitting in their car, listening to music, yeah? And if it's a song that you like, you can sing along, yeah? And you know all the words, right? You've got to play. You can't just sit there. You just sit there, I'm going to go like that. And you can generally sing the words as long as it's going on in the background. Then, as soon as the next song comes on, if I ask you to sing the song that you just sang, word perfect, you can't do it. In fact, you can't even start, right? And if I take away the music completely, you generally have a tough time. This is all about how the human brain works. Now, it's important for us to realise these lessons about the human brain, because communication is all about your brain and another person's brain getting together and agreeing on stuff. That's what communication is. So if you don't know how brains work, you're not going to be able to necessarily communicate properly. Every word I say in my head comes out perfectly, and everybody should understand it. But I don't live in your head, and I don't hear what you hear, right? And there's all sorts of interesting issues around that. There's language, right? So if English is not a language you're comfortable with, I can talk as clearly as I like, and there's going to be a barrier there. But there's all sorts of other things, right? I'm a statistician. I could start talking in the language of statistics, and we might have a problem there as well. And I might make crystal clear sense in full sentences around what I'm saying, and you might not understand one word of it. So there are these barriers. Graphics offer you one way to not have barriers, because we think most people see things the same. And I say people. But there are caveats to that as well. Is anybody here colourblind? No? Okay. It's interesting. There's about 8% of men have some form of colour blindness. All right? No women. Women don't have colour blindness. So if you're a girl, well done. Okay? One of the ways in this world that you get treated better than the men. I know the rest of the time it doesn't necessarily happen, and that's our fault. But yeah, no colour blindness in females. So red-green colour blindness is really common, okay? Which means that if you show graphics that require comparison of red and green, you're locking out some proportion of male viewers. Now, that may suit you just fine, but you've got to be aware of it. So these are the sorts of lessons that we're going to learn. Okay, so I'm talking about a few general things today, just to try and motivate where we're going. So this is maps, this is small multiples. You can look from one to the next, make those comparisons really easily. Okay, so basically what he does is he finds stories in the media. He either reproduces the graphics that the stories produce, or he produces his own graphics. So when the wife earns more than the husband, they report a smaller gap. Okay, and this is some graphics that do that comparison. Again, small multiples, there's only 2 of them, but you can look from one to the other and make the comparison really easily. And so on. Then there's things like this, the Marvel size chart. Right? So you've got Ant-Man down at one end and Giant Man down at the other end, and pretty much everything in between. I didn't even know there was Devil Dinosaur, but I just don't get out enough, I guess. All right. So there's Captain America. We talked about him yesterday. I don't know who the dog is. Who the hell's the dog? Yeah. So that's the Marvel size chart. The Marvel Cinematic Universe has a 3D network. Okay, so these are all different visualisations. They're fun to look at. This one's just a joke, right? So it's a bar chart, and it's about the percentage of warranty, the percentage of warranty time that's left, and then the failure rate. So nothing fails until the warranty runs out, and then the day the warranty runs out, everything fails. And you and I live that dream, right? Because you've all got smartphones, so you know how that works. So yeah. And so on. Okay, so we could spend 3 days looking at this, or more than that. I thought this one was really cool. Interactive to see street orientation everywhere. I'll take you to the site. So sometimes he points to external sites. Okay, so this is a guy who's made, and this is again spatial type data. So this is a guy who's made this stuff available. Okay, and he's got different cities you can look at. So let me see if I can make this. So let's go to Canberra. Now, so some cities are built on a grid, right? So all of the streets go right to left. Let's have a, well, before we look at Canberra, we'll look at Sydney. So we'll go to Sydney, zoom out, come to Australia, zoom in, all very cool. Okay, so we're in the Greater Sydney area. That's what streets are like in Sydney. They go almost every direction, but there is a dominant direction that's on a grid. Okay, so that's kind of interesting. All right, what do you reckon Canberra's going to look like? What do you reckon Canberra's going to look like? How long have you all been in Canberra? There we are. Streets going in every direction all the time, right? Now, I go running around streets of Canberra. Yeah, it's just never the case that you think, okay, if I turn down this street, I'm going to end up going in that direction. You never end up going in that direction. You're always turning around. It's weird. Okay? Then some cities are really built on strong grids. What's a good example? Where would you like to go? Tell me where you'd like to go. Someone call out a city. Paris, thank you. It's taking us to... There must be a Paris in Pennsylvania. Well, how whacked is that? Let's go to Paris, France, shall we? Yeah. So Paris has streets going every which way as well. A bit more like Canberra than you probably thought. Okay. And there are some cities that are definitely on a grid. So you can search for any city there. It tells you how he does it, and so on. So this is Detroit. Okay, and you can see Detroit. You can go in any one of 8 directions. That's about it, right? So it's just interesting. So these are different kinds of visualisations. Again, I'm not going to teach you how to do this stuff in this course, but one of the things I want you to take away from this course is an awareness of how powerful visualising is in terms of communicating information, okay? So yes, it's a stat course. At the end of the course, you'll know more statistics than you did before, but my broader goal for you is that you be a better communicator than you were before, because that skill is going to take you a lot further in life than knowing how to do an ANOVA table, I can guarantee you. Alrighty, so with that, that's today's fun. I know I spent a little bit more time on fun than I should, but hey, life is short. Okay, I'm going to show you how you can learn R yourself, and then I'm going to try and show you R where you can watch me do it. So there's a brilliant package called Swirl. Okay, it has a web page as well. It's called Swirl Stats. So you can actually point your browser to http www.swirlstats.com. Okay, Swirl, learn R in R. Okay, so if you want to learn R, you can go here and it steps you through how to do it. I'm going to show you how to do it anyway. Okay. So if you've just started up on R, then the first thing you're going to want to do in order to install Swirl is to type install.packages, brackets, quotes, swirl, close quotes, close brackets. Okay, so I did that before the lecture started because it takes about 5 minutes, 10 minutes, whatever. Okay, so we won't go through that again, but that's the first thing you do. Now R is a modular language in the sense that you've got a base package, but then there are literally 10,000 R packages you can download that do all manner of different things. This is the beauty of R. You want to do anything in statistics, odds are someone has already written an R package to do it. So that's gold right there. If someone hasn't, you can. And then you can submit that to the R network and your package can go live, right? So it's a really extensible language. So swirl is a package that's written in R. So the first thing you do is you install packages, install.packages swirl. Then in order to load it, you type library, brackets, swirl. No quotes this time. So you put quotes around it when you install things, no quotes when you load them. All right? So library swirl, so I'm going to do that. And when you do that, it says, hi, blah, 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 blah. See, so it's trying to be human and all that, pretending it knows you. Then it says, do this, do this. Then it says, type swirl, open brackets, close brackets, when you are ready to begin. Okay, so let's begin. Swirl, open brackets, close brackets. Okay, what shall I call you? Master. This is where you can live out those fantasies you don't want to tell anybody about. You know? Anyway, okay. So, thanks, Master. So it does what you say. Okay, let's cover a couple of quick housekeeping items, blah, blah, blah. When you see ... press enter, so you do that. Select 1, 2 or 3 and press enter. So you can kind of see it's going to tell you what to do. 1 is continue, so and it's fun too, right? 1 is continue, 2 is proceed, 3 is let's get going. So it doesn't matter what the hell you type. Okay, let's get started. All right. So then there are 4 basic packages that come built in, and then you can actually go onto the Swirl site and you can get more advanced stuff. Now, for us, if you want to get yourself going in R, or you've forgotten enough R that you want to get a refresher, and watching me doesn't do it for you, then install Swirl, load Swirl, try and get through 1 and 2. The basics of programming in R and regression models, basics of regression modelling in R. Those are the things that will make you kind of functional to get going. And we're going to cover the stuff that's in here later, don't worry, but this is a way for you to sit at home in your pyjamas, assuming you wear pyjamas, and get going on R yourself. And look, I just have to say to you, watching me do it will not, I mean, it'll help a little bit, but it's not going to teach you R, okay? You've got to do it yourself. So here's what I don't want to have happen, okay? Day before assignment's due. Come to my office. Can you teach me R? The answer is no. Not even if you bring $1 million. Okay? Because, you know, that's just not how it works. You have to do it yourself. This is an experiential thing. So have that experience. Okay? And Swirl makes it easy, so we type 1. Okay? It goes away, it loads that thing. Okay? R programming, so 1. And away we go. Basic building blocks, sequences of numbers, missing values, matrices and data frames. These are the stuff we're going to cover today, right? But you can do it all yourself in Swirl. So I really recommend you do that, okay? Now, how did I get out of that? I hit the escape key. People always ask me where the escape key is. Top right-hand corner of the keyboard, okay? Right up here. People laugh like you've never seen a keyboard before, but who uses escape, right? So it's there. Okay, so we're out of Swirl now. So we're going to do our own thing, but Swirl is terrific, and basically you learn at your own pace and you'll actually get somewhere very quickly, okay? So, all right, let's get back to what we were doing yesterday. Yesterday we were talking about using different data structures in R. We covered basic numbers, scalars. Now we're going to cover vectors. So a vector is a string of numbers. So 1 to 10 is a vector. It's got the numbers 1 through 10 in it. What a surprise. Okay. I'm going to give it a name. I'm going to say x equals 1 to 10. And then if I type x, I get that vector back. Now, suppose I wanted to know what the third element of x was. Okay, what's the third element of x? I'd go x square brackets 3. Okay, so square brackets are a special form in R, and what they do is they give you the element of a vector. Or, if you've got two things inside the square brackets, they'll give you the coordinates in a matrix. Okay? So we'll see that in a second. So x3 gives you that. Now you might say to yourself, okay, well, duh, right? The vector was 1 through 10, the third element is 3. Why are we doing this? What if you wanted to know what the third, fifth and sixth elements were? And I'm going to change it up a bit. I'm going to let x be a different vector now. So there's my new vector. And in doing that, I'm learning a new thing. This thing C is called it's a function. Most people think it stands for column because it creates a column of numbers, but it actually stands for concatenate, which is a very, very long English word meaning smush together. So if you concatenate lots of numbers, you put them all together into one object. So this says, put together into one object, C, these numbers. 1, 5, 4, 6, 8, 9, 10. Okay? If I type x now, it shows me that set of numbers, and it's a single object now, it's a vector. Now, if I wanted to know what the third through the sixth element of x were, I could say x, square brackets, 3, 6. That would give me the third, fourth, fifth and sixth elements. Now, this is where R, being an object-oriented language, starts to bite. Because inside that square brackets, I can put another object, and I have. That other object is the set of numbers 3, 4, 5, 6. Okay? And so that was putting one object in as an argument to another object. And this is what R lets you do. It's really powerful. Okay? What if I didn't want third, fourth, fifth, sixth, a contiguous set of numbers? What if I wanted to know what's the third one and what's the sixth one? How would I do that? I'd go x, square brackets, C, 3, 6. Oh, oops. I meant x when I said C, first one. Okay? So x says, look in the vector x and pick me out the elements that are the third and the sixth. Why have I got the C in there? Because I want the third and the sixth together, right? If I do this, if I go x square brackets 3, 6, because I want the third and the sixth, that won't work because x is a one-dimensional object. It's a vector, and I've given it two things. Okay? And so I get an error message. So R has two kinds of messages that it gives you. It gives you warnings, and it gives you errors. Now, most of you probably agree with me. Errors are bad, right? Something bad happened, and I'm being punished for it, so I don't get an answer. Okay? That's how errors work. Something bad happened, no answer for you. Okay? Warnings, you think, well, that's not too bad, I'm just getting a warning. It's like if the police pull you over and go, you were speeding, but I'm going to let you off this time. You feel a bit relieved, but you know what? It's not really that good in R. When you get a warning in R, it generally will do something, but it'll do something that's generally pretty dumb. Okay? So we'll talk about that in a second when we look at matrices. I'll show you a warning that occurs there. Okay? So that's vectors. Now, you can add vectors, x plus x. That'll just add element-wise. Right? You can divide vectors, x divided by x. That's kind of obvious. It should be a vector of ones. X minus x should be a vector of zeros. Right? So you can do all the obvious things with plus, minus, times and divides. Okay? So you can do... And the way R interprets these things is element by element. Okay? So that's easy. So those are vectors. Now what about matrices? Here's a matrix. I'm going to put the numbers 1 through 9 in a matrix. Okay? Numbers 1 through 9 in a matrix. X equals matrix 1 colon 9. What's that going to look like? thought you knew R. What's it going to look like? So, it's going to look like a column. Okay? Now, what could it look like? So this isn't a question to which you shouldn't know the answer. What could it look like? The numbers 1 through 9 in a matrix. If I say a matrix with the numbers 1 through 9, what pops into your head? A 3 by 3 array? Yeah? Yeah? Okay. So were people expecting to see 1, 2, 3, 4, 5, 6, 7, 8, 9? Is that what you're expecting to see, perhaps? Okay. Let's see if we can get it to do that. X equals matrix 1 to 9. Okay. N col equals 3. All right, let's see what happens. It's not 1, 2, 3, 4, 5, 6, 7, 8, 9 by row. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 by column. So it's still not what I wanted. Oh my God. Okay, what are we going to do now? X equals matrix 1 to 9, n col equals 3, by row equals t. And finally, there's the matrix I was hoping for. 1, 2, 3, 4, 5, 6, 7, 8, 9 by row. All right, now, that was a bit of a journey, right? I give you a simple task. I say, take the numbers 1 through 9, put them in a matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's like, I don't know, it's like childbirth. I'm told, it's so hard, right? And a question that must occur to you if you've never done this before is, well, okay, that's cool, but how did you know all this stuff? You know, how do you know to put n col equals, and how do you know to put by row equals? Because these aren't natural things, right? And the answer is, I use help. So help in R is wonderful. If I type help brackets matrix, I'll get you to watch over here, bottom right, your right, my left. Okay, help matrix. And over in this bottom right, you get R's help. Okay? And it tells you how to use it. Okay? Matrix, data equals NA. What does NA mean? NA means not available, missing. So if you don't give it any data, it just fills it up with missing values. That makes sense. N row equals 1. N col equals 1. By row equals false. So, n row, number of rows. N column, n col, number of columns. By row, fill it in, literally, fill it in by row. And this equal stuff is the default. So if you don't give it a number, it assumes n row is 1. And if you don't give it by row equals t or true, it assumes it's false. And that's why, when it created that matrix for us in the first place, it went down by columns, because it assumed by row equals false. And I know all this because if you keep scrolling down in the help, it tells it to you. Okay? So, use the help in R. It's really good. It'll give you information on every function you want to use. Now, beware, as always, right, that this is written by, you guessed it, statisticians and computer scientists. So this may not be in the English that the Queen might read, okay? So data, an optional data vector, and then it says, here we go, non-atomic classed R objects are coerced by as.vector and all attributes discarded. Did that mean anything to any of you? No, well it shouldn't. I mean, if it did, there's something wrong with you, okay? So non-atomic classed R objects are coerced by as.vector and all attributes discarded. So as.vector turns things into vectors, okay? It can't turn atomic or single unit objects into vectors. That's why it says that first bit. And then all attributes discarded. So if you gave it a matrix, what it would do is it would turn it into a vector just by putting everything in a big long column, or row, okay, and then it would discard the fact that it was a matrix. That's all it's saying. So you work, if you work with R long enough, you sort of get around the fact that nothing's in English or any language anyone wants to read, but you can generally nut out what it's trying to say. The following two at least are sensible. N row, the desired number of rows. Okay, I got that. N col, the desired number of columns. By row is logical. If false, the matrix is filled by columns, otherwise the matrix is filled by rows, etc. Okay? So that's how I knew how the matrix function worked. All right, now matrices. I've got a matrix X in here now, which looks like that. What if I want to pull out the middle element, the element that's in row 2, column 2? I would go X 2, 2. Okay, so you can refer to row and column elements by giving both the row number and the column number in that order, row, comma, column. Okay, row first, column second. What if I wanted the whole second row? The whole second row. How would I can even spell it right. The whole second row, I'd go X 2, comma. So I give it the 2, then I put a comma to say I've told you the row and I'm not telling you anything about columns, give me all of them. Okay? Second row, all the columns is the second row. Okay? If I want the third column, let's ask for the third column. You can probably tell me what to do now because what do I do? Comma 3, thank you. See? So you can pull out whole rows, you can pull out whole columns, you can pull out individual elements. Suppose I made a mistake and instead of having a 5 in the middle, I wanted a 15 in the middle. How would I do that? I'd go X 2, comma 2 equals 15. And now when I look at X, 15's in the middle. Okay? Now you can do lots of different things with matrices. You can add them together, X plus X, right? You can divide them, X divided by X. That's interesting. Did you know you could divide matrices? What about multiplying matrices? Who knows about matrix multiplication? A few people. All right. What happens if I go X times X? What does it do? It does it element-wise. And that's not what I wanted, because that's not matrix multiplication, right? If you want to do matrix multiplication, you have to go X, and then this is weird, percent star percent X. And that does matrix multiplication. Okay? So, like numbers and vectors, there are different operators that work between matrices. There's plus, minus, times, divides. But then there's this new operator, matrix multiplication, which is percent star percent. And you probably know about inverting matrices. How would I invert a matrix? There's a function that does that. It's called solve. If I go solve X, it will invert the matrix. Okay? Solve is a function that inverts matrices. All right, now, if I take a matrix and I multiply it by its inverse, what should I get? I should get the identity matrix. So let's do it. Let's go X, percent star percent, solve X. Okay, so I'm taking X and I'm matrix multiplying it by its matrix inverse. Okay? Oh, by the way, anybody who's losing a kidney because you didn't think matrices were in this course, don't worry. We're just talking about them because it's a type of object in R. We're not going to aggressively use matrices, so relax. Okay? So, what should I get? I should get the identity matrix. The identity matrix has ones down the middle, ones down the diagonal, and zeros everywhere else. This is what I get. Now, it's kind of right, and it's kind of appallingly wrong, right? So let's have a look. It goes 1.00000 e plus 0, 0. In other words, 1 times 10 to the 0, which is 1. So that's correct. That's 1. Tick, 1, tick, 1, tick. 0, tick, 0, tick. This number should be 0, but it's actually minus 4.4 times 10 to the minus 16, which, for those people who don't like using engineering notation, is 0.000000000000004. Right? That's what that number is. Right? Now, if you were talking to your mum, what would that number be? 0, right? Unless you're in Venezuela. Why do I say that? Because of inflation. Right? Venezuela's crazy, right? A loaf of bread, $1 billion. So, all right, so, and this is basically the fact that the computations that R has to do to multiply two matrices are kind of, there's a lot of multiplying and so on. And so it just gets things wrong in a very far out decimal place. So have you heard the expression good enough for government work? Yeah. So R will give you answers that are more or less right, but they can be out in like the 16th decimal place. For most purposes, this isn't a problem. Now, if you're trying to land the space shuttle, it might be, but if you're just trying to get from one end of the day to the other, probably not a problem. Okay, so that's matrix multiplication. All right, so very quickly we've covered scalars, vectors, matrices. Now let's cover lists. Here's something about matrices I didn't tell you. Matrices can only contain objects of the same type. So the matrix I've shown you is a matrix that's full of numbers. But not every data set is numbers. Suppose I have a data set which contains its first column is the age of a person. Its second column is the gender of a person. And its third column is an indicator of whether or not the person smokes. So such data sets exist, right? If you're trying to buy life insurance, that's exactly the sort of information they want about you. Your age, your gender, whether you smoke. Okay? Now, I cannot put that data into a matrix because the first column is a number, the second column is a category, and so, okay, some people think gender is continuous. Okay, that's cool, but it's still not a number, right? It's a thing. So I'm going to indulge the... So at the moment, my first column is numbers, usually between 0 and 100 because they're ages. My second column is genders. I'm going to call those M, F and O, O for other, okay? And my third column is, do you smoke or not, true or false, T or F. They're three different types, okay? So let's create this matrix very quickly. I'm going to do it for 3 people because you don't want to watch me type a whole lot of stuff. So X is going to be a matrix, okay? Now, its first element is, I'll create it by column. Its first column is age. So age is a vector which has, these people are 34, 76 and 12. Okay. The next column is gender. Gender, so in this particular data set, I've got a male as the first person, a female as the second person, and a female as the third person. Okay. And smoking is going to be, the male smokes, 34. The female doesn't smoke, and you've got a very naughty 12-year-old who's smoking. It's awful. Okay? So there's my 3 vectors. Now what I'm going to do is I'm going to smush them all together into a matrix. I'm going to force that to happen. I'm going to get X equals matrix. So how do I, sorry, I can do it a different way. I'm going to use something called C-bind, and I'm going to C-bind age, gender, and smoke. Okay? C-bind age, gender, and smoke. C-bind, C, column, bind, bind. Bind together columns. That's what it stands for. Let's have a look at X. Not capital X, X. No, have I hit caps lock? Oh my God, oh my God. There we go. There we go. Look what happened. Look what happened. Everything got the invisible bunny ears. Right? Don't you hate it when people do this? Of course you do. It's horrible. You know? How are you today? I'm well. That kind of stuff, right? So how old are you? 34. Right? So that's not a number anymore. And you know why? It can't be a number because I made it a matrix. And because I made it a matrix, everything inside it's got to be of the same type. And it couldn't turn M's and F's into numbers, so it had to turn the numbers into characters. And that's what it did. It turned everything into characters. And when something's a character, you can't use it as a number. If you try to use this as a number, try and multiply it by something, you don't get the answer you wanted. Right? 2 times 34. Error. Non-numeric argument to binary operator. Okay? Won't do it. So, if you want to mix types, we need a new type of object. Something that allows you to have a column of numbers and a column of letters and a column of booleans, trues and falses. Such an object is called a data frame. X equals data.frame, age equals age, gender equals gender, smoke equals smoke. Now look at what X looks like. Except I've written Jedna instead of gender, but that's okay. In these days of confused gender, it doesn't matter. This is genuinely confused gender. Okay, and now the first column is numbers, the second column is letters, and the third column is booleans. Okay? So that lets you create objects that have different kinds of types. So, data frames are an alternative to matrices. They're more flexible, they give you different types. You'll notice that I can name things, and in fact, if I take a data frame and I attach it, if I attach X, then I can use the names that I gave things. Okay? So I actually mistyped gender, I typed Jedna, so that's the name that it's given it. So if I attach X and I just type Jedna, right, I get MFF levels F and M. It's made it a factor. So that's pretty cool. Factor with 2 levels in this case, male and female. Okay? So those are data frames. All right, what next? In a data frame, everything has to be the same length, right? So in this data set, I had 3 people, right? What if I had different numbers of people in each column? Because that can happen with data sets. How would I handle that? For that, I need another kind of construct, which is called a list. Okay? So I could have a list, and so let's suppose that I wanted to create 3 variables, okay, which are the names of committee members for 3 committees. I could do that in a list, okay? So my committees are, it's a list, committee 1 equals C, it's going to be Mary and Fred, generic names. C2 is going to have 3 people in it. It's going to have Joe, John and Jebediah. I don't know. I'm no good at names. Whatever his name is. Badly misspelt. And so on. I could have a third one. I'm going to stop there because you're watching me type must be causing you pain. Okay? If I type committees, it gives me my 2 committees. Okay? They're of different lengths, and it doesn't matter that they're of different lengths. Okay? So lists let you combine objects of different lengths. They can also be of different types. Okay? The way you refer to elements of a list is using this dollars notation. If I look at committees dollars C1, it only gives me the first element. If I look at committees dollars C2, it gives me the second element. Okay? So when you see dollars, okay, it's telling you that you've got a list, and the name that comes after the dollar is the name of the list element. So lists are ways you can combine objects that both have different types and different lengths. So it's very flexible. All right, one more thing to cover today in the 1 minute we've got left, and then starting on next week we'll start talking about graphics. in R, and that's functions. Okay, functions in R. Now we've already seen a couple of functions. The thing matrix is a function. It takes in an argument and it produces an output. C is a function. It takes in an argument, it produces an output. Okay?